Hello everybody. This is going to be the last problem that we're going to solve in this chapter. And it's going to be like a more advanced problem than what we did before. The two problems that we solved before were very straightforward. We had two phases, and mass transfer is taking place between the two phases, either for absorption or stripping. And it was just this. But this problem is more interesting because it is putting the mass transfer problem in a big problem. So it's not only getting the interfacial concentrations or anything like this. It's more of solving a real problem, and this will be really helpful because it tells us how we can use it in real life applications, and how these concepts that we use can be applied in actual processes like the one that we see here. So just to see the big figure instead of just looking at the mass transfer process as an interfacial process, and that's it. So this process is the carbonization of water, which is inserting or increasing the concentration of carbon dioxide in water to produce soda water or something like the beverages that we usually drink. So we have here a gas phase and a liquid phase that are fed into this container continuously, and the two phases are in a case of a steady state. So there is in and there is out for the gas, there is in and there is out for the liquid. We have here the carbon dioxide is compressed in this gas phase into this tank that's filled with liquid water, and the gas phase over the liquid is well mixed. That's why I have this mixer here, and we will talk about the well mixed part and how this is important for us. And the CO2 composition exiting the space contains 10 mole% carbon dioxide. So we have here the mole fraction of carbon dioxide is 0.1, and the rest is nitrogen, which is 0.9. The pressure is 2 atmosphere, and the temperature is 25 degrees Celsius. And we have here the water that enters the container contains pure water. It's only pure water. It doesn't contain any no dissolved carbon dioxide. We know the flow rate, it's 0.2 meter cubes per hour. The liquid is well mixed as well. So we have here the gas is well mixed, the liquid is well mixed, but the gas is not bubbled into the liquid. So usually what happens in this kind of systems is that you have a liquid and the gas is bubbled through the liquid to increase the area of mass transfer and increase the turbulence and make the process more efficient. But in this case, for the sake of simplicity of calculations and to make it more convenient for us to solve, it is not a bubbled gas. However, the liquid surface defines the gas-liquid interface mass transfer area. So mass transfer is taking place through this interface. We know the diameter of the tank is 3 meters. The depth of the liquid, or the depth of the liquid is 1 meter. And we know that the nitrogen does not dissolve into the liquid, and the solvent is non-volatile. So as this is what we said before in the previous two cases, that the liquid is not transferring to the gas phase, and the nitrogen is not transferring into the liquid phase. So the only species diffusing is carbon dioxide. And we know that the Kc of the gas is 0.05. And keep in mind that this is Kc of the gas, it's not Kl, it's Kc of the gas. And we know the liquid mass transfer coefficient Kl, we know the value of Kl, and we know that the equilibrium follows Henry's law, and we know that Henry's law constant is 1630 atmospheres based on the definition of PA interface equal HX XA interface. So this is the equilibrium between partial pressure and mole fraction. We know that the density of liquid water is 25 degrees Celsius is 995.2 kilograms per meter cube, and we need to know the concentration of carbon dioxide that comes out with the liquid water exiting the tank. So we need to know how much carbon dioxide is gonna be coming out, or the concentration of carbon dioxide in the liquid water. So if you think about this is a mass transfer process, or part of this is mass transfer, because we have carbon dioxide, no carbon dioxide here, and there's carbon dioxide coming out, and there is carbon dioxide going inside. or diffusing from or transferring from the gas phase to the liquid phase, and that's why this is the mass transfer part of it. But if you want to look at the big picture, this is a very, very important thing, because sometimes people like to define the problem based on the topic. So if it is a mass transfer process, so it's a pure mass transfer process. If it's a heat transfer process, then it has to be a pure heat transfer process. But in actual life, it's never like this, and that's why I feel this problem is an important one, because in real life you don't split the parameters, because all the parameters are affecting the system. So it might be simultaneous heat and mass transfer, it could be mass transfer and mass balance, it could be anything. And in this case, to be able to solve this problem, you have to look at the big picture, or to have a strategy of solution. And the strategy of solution has to be defined based on the required output. So the required output is the concentration of carbon dioxide coming out. So keep away from your mind the details of mass transfer now. Just think of this: if I have all this available information and I need to know how much or what is the concentration of carbon dioxide coming out, this would be a very, very simple and straightforward mass balance equation. So here you would say that there is carbon dioxide in. If you do mass balance on the liquid in the tank, then you have carbon dioxide going with the liquid stream, which is 0, and you have carbon dioxide going from here to here, and you have carbon dioxide coming out. So you do simple mass balance and you can get everything done. But there is, and this is what we are gonna do. And when we do this or we do this equation, you would see that there is a mass transfer term inside, which would be the mass transfer part of the solution. So this is how you think of this, how you can think of this. But before we go through all these details, I need to take a few minutes or a couple of minutes to talk about the perfect mixing in the gas and the liquid phase, how this is gonna be important for us. The perfect mixing, I think we mentioned this before in the diffusion, but I'll repeat it again. The perfect mixing is a model of the tanks in general. It's one of the models that describes tanks or flow inside tanks. So when you do perfect mixing, you assume that the concentration everywhere is, and that's why it's called perfect mixing, because you're mixing it perfectly so that the contents of the tank are homogeneous everywhere. So the concentration here and here and here and here are all the same. You have the same concentration everywhere, the same temperature, the same pressure. So it's exactly the same thing, because you are mixing this perfectly. You also consider that the feed concentration is not affecting the concentration inside the tank a lot. It's almost not affecting it, because usually in these kind of tanks you assume that the amount that you feed into the tank are quickly mixed with the contents of the tank, and it's not changing the concentration. So it's always the same, and the stream coming out of the tank has the same concentration as what's inside the tank. So this is the case here and here, and that's why we were given the information about the stream coming out of the tank, not going into the tank. So by knowing that this is perfectly mixed, and by knowing that this is the outlet concentration, we can tell that the concentration inside the inside the tank in the gas phase is what we have here. And by doing this, because this is a very, very important part of the solution as well, that the concentration coming outside the tank is the same as the concentration inside the tank. So this is very important to keep in mind. And I'm talking about this in details because in the textbook these details are not discussed, and I think they assume that these points are already well understood. So this is what we mean by perfect mixing. So again, the strategy of solution is gonna be writing the balance equation. I put the general form of the equation, which is the rate of carbon dioxide with the inlet stream, plus the rate of carbon dioxide transferred from the gas phase, which is going inside the liquid phase, and this is the rate of carbon dioxide in the outlet stream plus the rate of carbon dioxide produced equals the rate of accumulation. We will put some assumption here that we have steady state, we have no reaction, and we have as we said, there is perfect mixing, which means that the concentration of carbon dioxide in the outlet stream equals the concentration inside the carbonator or inside the tank. The liquid volume is constant, the concentration of carbon dioxide in water is very low, and we will see why these two are important for us. But this will be later. So based on all this information, we can cancel these two terms of the accumulation and the production, and then we will end up with these three terms. If we want to substitute the rate of carbon dioxide in the inlet stream is the flow rate multiplied by the concentration. So this is QCAN and this is QCA out, which is out, and this is the rate of carbon dioxide is the flux multiplied by the cross-sectional area. Now we need to see what are the information that we need to know in order to get all the parameters except the concentration out, and then we will be able to get the concentration out. So this is the main goal now, is to see first what is the expression of the flux, and to get all other parameters that we don't know. Now if we go to the flux equation, we have four options if we want to calculate the flux. We have the option of using individual mass transfer coefficients and the overall mass transfer coefficient. We have the option of using this in the gas phase and in the liquid phase, and that's why we have these four options: individual in the liquid phase, overall in the in the gas phase, overall in the liquid, overall in the gas phase. This is individual in the gas phase, overall, individual in the liquid phase, overall in the liquid phase. So these are the four options that we have, and this part is not discussed in the textbook, and that's why I believe this is important. In the textbook, they picked the equation and they used it directly without going through this discussion. So this might be a bit confusing why you choose one of these four. But to understand this, we have to exclude some of them. So if we go back here, the equation here is in terms of concentration, and we are interested or doing balance on the liquid phase. So it doesn't make any sense to use any of these two equations. So we will cancel these two. We will not consider these as options because we will add more variables than what we already have. So I need to have an equation that contains the same variables that we have. Like these two, if you see these two equations contain CA out, which is the same parameter that we have. And here the difference is in KL and CAI, KL and C star. So if we want to pick one of these two equations, we need to see which is going to be easier for us to use. And this is the criteria that we can depend on for choosing the equation to use. And to do this, we need to check what are the information that we don't know. So if we check the two equations, we will see that C out is the parameter that we want to calculate. We don't know the interfacial concentration, but we know KL. In the second equation, we need CA out. We don't know the overall transfer coefficient, and we don't know CA star. Because KL is given, so we already know this, and this is the only variable that we don't know here, and these are two variables that we don't know here. So simple logic will say that, okay, I'll go for the third equation, which is this, because it makes more sense. I just want to get one parameter, while here we will get two parameters. So if we check this, then we will see that getting C interface is not easy. We have done this many times before in the discussion and in the two problems that we solved. So the interfacial concentration can be got by solving the mass balance equation with the equilibrium relation. So this is what we will have. This is KLCAI minus CA. This is the liquid phase mass transfer flux, and this is the gas phase mass transfer flux. We substitute Kg with P interface with HC interface. Then we will rearrange the equation in order to get C interface in terms of the rest of the parameters. And if you plug this in here, the equation would be this. So this is how we can get the flux in terms of CA interface and KL. So you see here that this is kind of not an easy to use equation. Plus we have CA out here in two places, here and here. And if you check or you remember the mass balance equation, we have already C out in the last term in the equation. So now we will have an equation that contains C out three times or in three different terms. However, if we check the other case, we would see that the KL and C interface and C star are very easy to get. For KL, you can get it from the relation, because this is a linear relation. The equilibrium relation is a linear relation, so we can get it from KL HKG over KL plus HKG, which is another form of this equation. So this is very straightforward. It's gonna be direct substitutions in the equation. You get KL very simply. The other parameter, which is C star, is simply you can get it from the equilibrium relation and the bulk gas phase partial pressure. It's going to be PA divided by H. So these two parameters can be easily calculated in one step without the need of getting an equation that is in terms of the other parameter that we need to calculate. So that's why this is more easy to use, despite the fact that this has one parameter that we don't know and this has two parameters. And this is the equation that has been used in the textbook without this discussion. So I believe this is important for you to understand on what basis this equation was chosen. I'm gonna do the solution for, or the next steps for the two equations to show you that both are gonna give the same output. So for the first option, which is substitution with the local or the individual mass transfer coefficient in the liquid phase, this is gonna be the equation. We substitute with C interface with this bracket or this term. Then you would see we have here CA out, CA out, CA out. So we have to rearrange the equation in order to get CA out in terms of the rest of the parameters. So this is CA out plus O multiplied by all these three parameters equals these two parameters, and this is the equation that we will get. You'll see it's not friendly to use. It's very complicated and it's not gonna be easy, and there is a big chance of doing mistakes while doing all these divisions inside the numerator and in the denominator. But this, as you see, this is gonna be directly substitution or solved by direct substitution. You have Q, you have CN, you have KL, KG can be calculated, S can be calculated. So all the parameters that we have here can be easily calculated. But I'm talking about the mathematical steps of the derivation and the mathematical calculation of the outlet concentration. However, if you check the other option, you would see that it is gonna be very straightforward. You already calculated Kn, you already calculated Ca star, so it's gonna be as simple as this. So if you compare these two equations, you'll see that this is much more easier to use than this equation. Okay, and by the way, if you do some mathematics or some comparison of the terms that you have here and the terms that you have here, you would find that this term KL KG S divided by KL plus H KG multiplied by PA, this term is the same as this term. So that the numerator is the same. For the denominator, you'd see that these two terms are the same as this term. So it's the same equation, more or less the same. But in this case, I get it in a simplified form by calculating Ca star and KL directly, instead of going through all these. So anyway, so this is how you can tackle this problem. I'm gonna go through the rest of the solution with this equation because it's easier to use and it's gonna be more convenient to use. So I have here all the parameters: the pressure, the temperature, XA, YA, Q in terms of meter cube per hour and per second. I have Kc for the gas phase. I have KL, raw water, D and L. So if we want to get back here and see what are the parameters that we don't know. I know the Q, I know CAN is 0, I know we need to calculate S, which is the cross-section area, we need to calculate KL and CA star. So these are the three parameters that we need to calculate: CA star, S and KL. If we know them, we're done. So to do this, we need to first unify the units. So for KC that we have here, it's for the gas phase, so Kg can be calculated using Kc, which is Kc over RT. You can go through the derivation that we did before, but for the sake of time, I just put this equation here. For the equilibrium relation, we said that it's put in the terms of Hx, which is the relation between partial pressure, and X, which is mole fraction. But the equation that we used to get KL in terms of the individual or the overall mass transfer coefficient in terms of the individual mass transfer coefficients is between P and C, or partial pressure and concentration. So we have to unify the units to convert this Hx into H. So to do this, we will need to get CL, and again with the assumption, and this takes us back to the assumptions that we made, that the concentration is very small in water, so we can assume that the total liquid concentration is the density divided by the molecular weight of water, so this is CL. And now we can rearrange or rewrite the equation as Hx multiplied by Xa. Xa is Ca divided by Cl, so it's going to be Hx divided by Cl, which is H. So now we have Henry's constant, and now we can calculate the overall mass transfer coefficient, which is 1.5, almost 1.5 times 10 to the minus 5 meters per second. So this is KL. And now we need to calculate the cross-sectional area, which is pi over 4d squared. And by the way, this is the normal cross-sectional area. If you go back to the to the problem itself, you would see that the mass transfer is taking place in this direction from top to the bottom. So the cross-sectional area that is perpendicular to the flow, or the normal cross-section area, is the cross-section area of the tank, which is a circular tank, so it's pi over 4d squared. So this is how we calculate the cross-sectional area. So we can calculate it. CAN is 0, and for C star it's simply calculated from PA divided by H. PA is the partial pressure, which is total pressure multiplied by the mole fraction divided by Henry's constant, which is this constant that we calculated here. And now we have C star. So we have everything now. You just need to make sure that the units are homogeneous. So if this is kilogram mole per hour, then this has to be in kilogram moles per hour, and I mean per meter cube. So the units must be homogeneous. So if you substitute, you will find that the outlet concentration is 4.461 gram mole per meter cube. So this is all what we have to do in order to get the outlet concentration. The most important part that I want to emphasize here is that we don't consider the problem as a pure mass transfer problem. We have here a combination between mass transfer and heat transfer. So you have to, and mass balance. So you have to make sure that you have a good understanding of the problem, and to have the flexibility of thinking of the way of solving the problem, and to put the strategy. I believe that this is a very, very good part of it, is that you put the strategy of solution, you get the solution or the problem steps, or the solution of the problem steps done already before you start, so you know what is your next step and where you are going with this solution. So this is all for this chapter, and we have only one more chapter left, which is going to be the topic of next video, inshallah. Goodbye.